Welcome to Snow Basin. We're talking timing today. My name's Ted Savage. I work for the Olympic Organizing Committee as a timing and technology specialist for the Olympic Games. And here at Snow Basin we're doing an alpine downhill event, which is a fairly complex timing operation because of the number of timing points that there are. And we're going to describe to you what we do. We have behind me over here a setup of the hill wire that comes in from the hill. Out on the hill we have sensors being either start gates, photocells at intermediate points, or photocells at the finish line, which provide us with the timing data that allows us to compute the times on course for every skier. We have to get those sensor impulses from the photocells and the start gates down the mountain by a wiring infrastructure, a whole bunch of wires, into the timing building and then connected to the two timing systems that we use, System A and System B. Those two timing systems are approved, certified devices and follow very concise specifications and not only time but also provide us with a printed copy of what happens at the timer level. And that data goes across to the computers, which crunch the numbers, which produce the times on course and the intermediate times and the speeds, and output that to display boards, to commentator information systems, to smaller display boards at the finish area, and our hard copy results systems that the race secretariat provides. So we're going to take you on a tour on how all that gets in here. From the sensor level, the photocells and the start gates are basically switches. They work on a normally open contact, which means that normally they're open, and when an event occurs, like when a start gate opens or a start gate or a photocell triggers, the wire pair that we're connected to at the end of the timing system goes from a normally open condition to a short and then open again. That's what provides the trigger, that normally open trigger, whether it's a start gate or a photocell. That trigger on every discrete wire pair comes down the mountain and comes in to us through a patch panel that allows us to route either the primary or the backup impulses from those sensors to the two timing systems. The two timing systems operate in time of day. They don't start at zero and run up for every skier. They are constantly running. They're synchronized to the time of day. We have a little GPS that gives us the exact time of day so that we can synchronize to that at the beginning of the session. And those two timing systems run in a synchronized time of day. And every time an impulse is received from either a start gate, a photocell at an intermediate or a speed trap, or the photocell at the finish, or photocells at the finish, those impulses are routed to those timers, and when they trigger and give us data in time of day. Time of day to the 1/1000th of a second. That data is broadcast, in our particular case, on a local area network, a LAN, which connects to the computers, which crunch the numbers. They take the start time in the rudimentary sense. They take the time of the start at time of day, subtract it from the time of the finish in time of day, and produce the time on course. So you're not constantly resetting clocks. What is actually happening is every time a sensor triggers out on the race course, it's generating a time in time of day. That time of day is going to a computer. The computer is doing the math very rapidly and producing the time either on course or at an intermediate point or a speed, and outputting that information to either a scoreboard, a printer, a commentator information system, or some other peripheral device that provides the information to the people who are watching. We're going to take you on a tour of how all of that works outside on the hill and inside here in the timing building, so you gain an appreciation for what it is that the timing volunteers out on the hill do in order to make all of this work. Because if the hill isn't solid and we're not getting the right information from the hill through the wiring system to the timers, to the computers, and out to the display boards, you have to start with a very solid base of information, and that solid base of information is what happens out on the hill. This is the patch panel for the wiring system coming in from the hill. These are 25 pair connection points for the cables that we have coming either from the A cable or the B cable going up the mountain, or the A finish or the B finish coming across from the finish line. So we have many pairs. Each one of these little connector points that is color coded represents a pair of wires that we can take these clips and associate with a specific pair of wires. This is called a CT110 block. It's widely used in North America as a telecom solution. It's one which we've adopted throughout the network here at Snowbasin. This information, this is where the timing systems connect to the outside world. Once the wiring connects us to the hill, it flows back into these devices which are known as optocouplers. If you had to invent probably the best antenna in the world, it would look something like the wire that we've run up the mountain. And that's basically what it is we've got a couple of miles or many miles of cabling that go up the mountain to which we connect the timing systems. There's a risk of lightning strike, there's a risk of all kinds of noise being gathered by the wiring that's up the hill. These devices here allow us to interface to the timing systems. They're typically called optocouplers, and because we have so many functions at Snowbasin, for example, we have on a downhill course you have start, intermediate 1, speed at 1, intermediate 2, speed at 2, intermediate 3, intermediate 4, and the finish line. So you'll have from 8 to 9 functions for system A and system B, and all of those connection points have to come in and be sorted out by channel identification and then routed onto the timers. Each function has a channel, and those channels are available from 1 to 18 on these boxes, and they're also optocoupled. Optocoupled means that they're physically disconnected from the hill, and the way in which the trigger from each sensor gets through to the timing system is by jumping across a small space in a chip, and that means it optically couples the connection from the hill to the timers so that there's no physical connection which removes any chance of interference from electrical noise or electronic noise that's being picked up by these two great antennas that we've got up the hill as represented by the hill wiring. So these optocouplers have all of these channels to which we plug in the various functions from either the start, intermediates, or the finish, and then those are routed on to the timers. The two timing systems then take the information that is coming in from the hill on the various channels, and we assign the various functions, whether it's start, an intermediate point, a speed trap, or a finish line impulse, to either system A or system B. The two timing systems are running in synchronized time of day, and which means, for example, here it's 10:40 in the morning and we have the time of day running. Every time an impulse comes in, every time the timing system triggers, the printer prints, and the timing system sends by a data link to the computers a time of day down to the thousandth of a second. That's the kind of information, the fundamental information that we need from each point, whether it's a start, intermediate, speed trap, or finish, in order to do the calculations at the computer level to compute the time on course. The reason we have two systems, of course, is in case one of them fails. That does happen, either because the connection to the timing point, whether or not it's the wire or some other factor, prevents the timing signal from getting in here, so that we don't have it on system A, we'll have it on system B. We have two different pairs or two different cables going up the mountain, two different timing systems and two different computer systems running in parallel to assure that if something goes wrong at one system, you'll have it on the other. And they both operate, as I say, in synchronized time of day. The printers are essential at the timer level because they are dedicated and attached directly to the timers to print exactly what comes out of the timer when it occurs, so that if at the computer level something goes wrong, we have all of the data that we need on the tapes and also in the memory of the timing device to be able to backtrack and get all of the information and do the calculations necessary to calculate any result from system A or system B. So we're backed up in terms of whether or not the computers work or not. At the timer level as well, we can disconnect any of the power, and even though the external supply has gone off, with the internal batteries the timers will continue to run. So power can fail, the computers can go down, and it doesn't matter as long as we have the information that comes from the various timing points indicated in time of day, and that's what happens with every timing impulse that comes in from the hill. It either gets recorded on System A or System B and simultaneously printed and broadcast on the network to the computers, which do the more refined calculations and produce the run times and all of the data that goes out to the rest of the world. Once the timers do their job, timers just time. They just time in time of day. And the data will come across to the computer, which is going to do the work. The computer is set up to look at starts, intermediates, and finishes, and to bring in the data that comes in from the timer that it's connected to. We have a System A and a System B. Every time a time comes in, it's assigned to a skier. So when the start gate triggers, you'll get a time of day to the thousandth of a second, which will come in over here. That time of day, if it's assigned to bib 1, will be kept in memory as for the start time for bib 1. When ultimately the finish for bib number 1 arrives, in a fraction of a second the computer will compare the two times one to the other, time of day start to time of day finish, and produce the time on course. It'll also do that exactly the same thing for intermediates, speed traps, whatever it is that we have configured on the timing software. Whatever we ask it to do, it will do. Once it has the time at that particular point calculated, whether it's an intermediate point, a speed trap, or a finish line time, and then that time on course, it will send that information to the results grid, it'll send it to the display board, it'll send it to the commentator information system, it'll send it to a dedicated logging printer, and ultimately when we print results, or simultaneously as we print results, it'll keep updating hard copies. The computer is very powerful to do all of that kind of thing, and you can make infinite changes on it. You can drive various types of devices, you can do all types of different things with it, and that's why we separate the functions of what the timer does from what the computer does. The computer computes, the timer times. We have anything can happen at this level, anything can go wrong at this level, and the timing data is assured, it's saved, because at the timer level we have it all in memory, plus we have it on the tape, plus we have two of them. So the functionality of what happens on the timing on the computer system is a function of what we ask it to do. At each timing point, whether it's the start, the intermediates, the speed traps, or the finishes, we have people assigned there who are talking to us on communication systems. And the operator simply has to look at the screen and manage what's going on the race hill based on what he's hearing on the headsets and what's coming in from the timing systems. So one person can basically do this job and manage a very complex system because the software allows a graphic representation of what's going on the hill. One of the keys to understanding what's going on out there when we talk to you in the timing building or talking to any of the people that are manning the timing points, whether it's a start position or an intermediate point or the finish line, because we're so removed from it, is using headsets to communicate. And we've broken those down into different channel paths so that we can listen to what's going on. The person running the software and trying to control the hill and what the functionality of what's going on at the computer level needs to understand where the athletes are on the race course or what's going on the race course at any given time. Photocells can go out of alignment because of wind. There can be course workers on the hill that cause problems. There can be directions that we need to either give or receive. So we use a communication system to bind all of that together and to understand what's going on. The headsets are actually quite robust. But they are eventually breakable, as is anything. But this is another type of connection that we plug into the hill wiring system that allows us to understand what's going on from a voice point of view. And it's a very specific protocol that we develop between the people out on the hill and the people inside the building in terms of the types of words and phrases that are used in order to understand what's going on out there, because with 4 intermediate points, 2 speed traps, a start and a finish, there's an awful lot happening as the race is going on, and it's important to understand at the computer level where the athlete is and what's going on precisely at the hill. So communication is a very important part of what we do. One of the most important things that this software will do is generate television graphics. It's something that we haven't talked about. It's one of the most complicated elements that is finally output from the timing system. Timing system, as I say, will output to things like display boards, either the giant matrix display board that we have here at Snowbasin, or the one-line displays. One of the most important elements that is produced out of the timing system is the television graphics that get sent to the TV production. The screen that you're seeing here is a representation of what we send to television from the timing system, and is directly linked to the computers, which are directly linked to the timers. So it's live. It gets produced the instant it receives any information, which is crucial to producing a good television show. And having the timing information on it is very important. The running time, which is down in the lower right-hand corner here, is referenced to the time already achieved by the leader on course, which is in the left-hand side. That information is overlaid onto the screen that's being shot by the cameras that are positioned on course. So the timing information gets overlaid onto it. We produce it here, and much like the type of information that gets sent to the display boards that we have, the giant matrix display, the main screens that we have for the commentator information system. This particular screen, the television graphics that get produced by a separate device, contain the same type of information that gets sent to all of those other type of peripheral systems. So when a volunteer or a timing technician out on the course activates a photocell, immediately when that data is received, it is generated for the television production, which is produced here on this, which is what we see on this monitor here, but is simultaneously sent to the production truck. Even though we have all of these A and B electronic systems, there are things that still can go wrong. For example, a wand can break. Something can happen at the finish line where the photocells are obscured, and when the racer goes through, we don't get a pulse. So when all else fails, we have to resort to hand timing. And the head of hand timing, the guru of hand timing, is Alan Church. And I'll let Alan describe what the hand timing operation does in order to back up the electronic systems.
With the hand timing, we have a pair of timers at the start and a pair of timers at the finish. I'm using backups even for them. We have a recorder who works with them, and they have a pair of watches which are synchronized top and bottom, and when the racer leaves the start, they will operate the stopwatch and record what's known as a split time. It's again a time of day. We'll record that time of day on paper, so we have control of that right away. We also then, when that racer gets to the finish, we have another timer who will operate a synchronized watch and will record that time of day. We take the difference between these, and again we are able to get an elapsed time and compare that then with make up a time for the racer which is acceptable to the FIS from those times. We plot these data on a computer that we have in communication with the start and with the finish. We plot the data on the computer. We enter the data first, and we have then a plot which shows down here, and this, which shows the differentials between the electronic times and the hand times that we've used to calculate the same kind of data. And we use this then to calculate, to evaluate how well we're doing, how well our hand times are working, and also to unify the program for the electronics and hand times.
And basically it's an infrared beam that goes across. We have primary and backup here. And so what we do is line one up at a time so we don't get any cross beam. And this gives us our timing system finish line from both primary and backup. So right now I'm just trying to align the infrared beams and make sure that we've got a straight, accurate line. It means I get to run back and forth a lot too.
Women's start of the Olympic downhill. We're trying to get a NORAM off up here, and this is our start gate system. Talking about redundancy, we're looking at the two contacts, the two pairs of wires that are connected to the hill system. Two pairs of wires, two separate mechanical contacts inside the wand, and one wand, so that's the reference point in timing. The athlete leaves the gate, and when they do, we set it just below the knee. measure it with the type of athlete that we're dealing with when they leave the gate on course. And we have two of everything starting from here on back to the timing building. We only have one. We only want one because we only want one reference point in terms of where they leave the gate. That's very important, not to have two. We don't do that anymore. So athlete leaves the gate and the wand opens, two triggers down to the cooling systems on two sets of cables down the middle. The athletes need a reference in the speed sports, everything except slalom. Giant slalom, super G, and downhill all start on a fixed interval. So what we use is a clock that is set to the time of day, which triggers a countdown at 10 seconds to the start time, and also gives you a visual indication as well as an audible beep from 5 seconds to go. The athlete is allowed to leave the start 5 seconds before to 5 seconds after the assigned start time. That's also part of a safety contract that we have with our course workers. They see a racer go by, they know they're on a 1 minute interval, they know they have another minute to go out there and work until the next athlete comes along. 10 seconds before the start, we get a warning tone, and then countdown. And now on course. The athlete will leave the gate, and that's all she wrote.
Can't go now, but be ready to go on the next one. I made a quick note.
4, 3, 2.
Right on 5 on 4.
5, 4, 3, 2. One of the things we've been experimenting with and that we know is that that's a mechanical start gate. The problem with a mechanical start gate is it has a lot of slop. We're looking at what we've been doing the last 5 years with the FIS. We've been putting out photocells a little bit outside of the start. 1 meter, 1.5 meters, 2 meters, 2.5 meters out of the start in order to record optically their actual start time. So much like in bobsleigh and luge, we might have in the future have start times that are taken from photocells set right outside of the gate, so that it's a lot fairer for the athletes instead of incorporating mechanical slop into the start gate, which is part and parcel of what we do right now.
Are on.
This is Jim, our starter. Jim runs the start along with the start referee, Rob, over in the corner here. What's going on with Jim is that he's communicating back down to us on a dedicated headset what's happening at the start, obviously, and giving the start commands to the athlete as well as controlling what's going on. We need to know which bib number